we're all trying to be experts. That's why we come to seminars like this, to try and learn the latest developments. But it means that in cases where we don't have a lot of experience, we really need to have a certain number of large scale or full scale tests to tell us how the world really works. And once we've decided that, we can fit our models so that they match the behavior of the real world. And I think that's pretty critical for engineering design. In order to have the resources to do that, we had a NCHRP project that we performed. Dan Brown and I were the co-PIs. We also appreciated the work that was done by our in-kind contributions by Hayward Baker, now Keller, from jet grouting and soil mixing, and from rammed aggregate piers by GeoPier Foundation Company. Our test site was, wow, I've got it in the wrong place. Let's move on for that. It was in Salt Lake City, as we'll look at here a little later. Our research approach was to conduct full-scale lateral pile group tests and use a variety of soil treatment methods to evaluate the improvement that we might get. Would this be something significant or something that just doesn't work very well? Then what we wanted to do is calibrate numerical models and perform virtual, what we'll call virtual load tests, to evaluate different treatment parameters and geometries. We can't do full-scale tests on everything, but hopefully once we've calibrated our numerical models, we can use them to expand our database of test results. And then based on the full-scale testing and the computer modeling, we wanted to develop some simplified models that people could use in design. And so that's our end goal. This test site is located in Salt Lake City, Utah, and we did it within the right-of-way for an interchange on Interstate 15. We have here soft clay, mostly in the profile. The good thing about it, it's fairly consistent across the site, as you'll see. There was some compacted gravel fill at the surface, made it possible for heavy equipment to access the site without getting bogged down. So we could bring pile driving equipment and so forth without crane mats and things. We had access to water for our soil improvement techniques that needed this, so we could drive piles and use the soil improvement methods without having to rip them out and demolish them at the end. So it was a great site for us to do this testing. We put in a number of pile groups. These were typically piles in a 3x3 arrangement with 9 12.75-inch OD steel pipe piles. And we ended up doing something like 16 lateral pile group load tests. First, we did tests with untreated virgin clay around the piles for a control section to compare against. And we did test with compacted fill as a soil improvement, test with jet grouting around and within the pile, tests involving soil mixing of different types, flowable fill on one side, and rammed aggregate pier geometries. We're going to focus on these first 3 or 4 here in this presentation, which were some of the most effective. And I always, when I would go to these seminars like this, I always like to have something that I can look back on. So if you look up this NCHRP report 697, you'll find the report that gives all the information and references that I'm going to talk about here. And I was the lead author with Dan Brown as the co-author on this study. You can download it freely on the internet. This is the soil profile that we're looking at. We have cohesive soil down to about 7 meters, or what, about 25, 30 feet or so, something like that over here. The PI was on the order of 15 to 20%. We have an undrained shear strength that we define from unconfined compressive strength testing, Torvane, CPT, and other testing where we've got maybe 1,000 PSF in the top 1.5 feet due to desiccation. And then we have zone below that going down to maybe 20 feet where we have undrained strength from 300 to 600 pounds per square foot. So fairly weak material. Since we're going to be comparing site to site with different improvement techniques, we wanted to see how uniform our soil profile was. So we did CPTs at each of these 4 test sites. And you can see that from the cone resistance that we're getting very consistent behavior. We have a few sand lenses, but the clay behavior is, and the site is very uniform across its, in the horizontal direction. So let's look at the pile group layout. Like we discussed, we have a 3x3 pile group arrangement. They're spaced 3 feet on centers. So they're a little tighter than maybe you might see sometimes. 2.8 diameter pile diameter spacing. These are 12.75-inch steel pipe piles filled with concrete. We have a pile cap on the top of them. It was about 9.5 feet square and 2.5 feet deep. And the pile cap was poured flush with the excavation, and then we excavated on the front and back, excavated on the sides to create a gap so that we're only looking at passive resistance on the front. We're not looking at adhesion on the sides. It makes it easier for comparisons. We have a corbel on the top of the pile cap that allowed us to mount a hydraulic or MTS actuator so we could push and pull these pile caps against one another to do the load test. So in the untreated soil to begin with, in test 1, we used this actuator to pull the 2 pile groups together. And that way we're seeing passive resistance on the front face of the cap. And then in the second test, we pushed them apart. And we have excavated on the side of this cap here so that we could isolate the passive force we were getting. And we'll look at that here in just a minute. This is a photograph of that. You can see the corbel. We got Dewey dag bars to connect on this actuator that had a 600 kip capacity. And then we've got extension rams or extension struts that go out. These are about 25 feet apart, something like that, so that they are not interfering with one another. Then we're monitoring the deflection of the pile versus depth with inclinometer and shape arrays, and monitoring strain in the pile for bending moment, and monitoring load versus deflection from independent reference frames. This plot shows the load versus deflection from those 2 pile caps in untreated soil. As I indicated, we were pushing them against one another, so they are moving in opposite directions. And we loaded them incrementally, and then so that we could get values at 1/8 of an inch, 1/4 of an inch, 1/2 an inch, out to about 1.5 inches. And then at the end of each peak, we would do 5 cycles of loading to see what kind of cyclic resistance we'd get at that point. So we were concerned to see what kind of consistency we'd get from one cap to the next. So on the next slide, I'm just going to switch the directions so that we can compare them against each other side by side. And to my mind, that's remarkable agreement from 2 separate piles, pile caps, considering the variations in pile driving and so forth, that tells us we have some really consistent profiles, giving us remarkably consistent load versus deflection curves. We're getting about 275 kips of capacity, and it turns out that about 50 kips of that is due to passive force on the pile cap on the front face there. So the simplest thing we could think to do was to use compacted fill. So prior to installing one of the pile caps, we excavated the clay away from around the pile cap, or around the piles, and put compacted granular material. So this is just sand. We excavated down 3 feet below the base of the pile cap, compacted the sand. The sand extends out 6 feet in front of the piles on one side and just 1 foot out in front on the other side. And we'll load in both directions and compare that against what we got from the untreated native soil. So here you see the excavation. We're compacting with the compactor on the trackhoe around the piles. We're getting something a little less than what you might want to get. We're only getting about, on average, like 94% of the Proctor maximum density. So that's about 104 pounds per cubic foot. And here we see it just before we built the pile cap in place. So this is the side with 6 feet of sand, and this is the side with 1. And we looked at the results from our test with the compacted fill extending 1 foot in front of the pile cap. We get about a 10% increase in lateral pile group resistance for this case. And if we have it extending out 6 feet in front of the cap, 20% increase in lateral pile group resistance. So these are pretty mild or pretty low increases in lateral resistance. Might be useful in some cases where you just need a little bit extra, but you also have to recognize that it's a fairly low cost, low tech improvement strategy. We had another test site at the Salt Lake Airport where we could do some additional testing. We had here a load frame with a group of piles. There's 15 piles in a 3x5 pile group arrangement. We loaded in clay laterally and got our load displacement curve. And then we excavated 3 feet down into the clay and filled that back with sand, and then added additional sand. So now that we have a compacted sand layer that's 8 feet thick around our pile group. Put our load frame in place again and did a lateral load test on this group. Now where most of the resistance is coming from this 8 feet of compacted sand. So here you see the total load versus pile group deflection. And we're seeing, in this case, about a 30% increase in lateral resistance as a result of that 8 feet of compacted fill. Now, as you might imagine, this depends, the increases you're going to see depends on the change in strength that you get. So for the 2 tests that we were talking about, that 30% increase was from going from a clay with an undrained strength of 900 pounds per square foot to a compacted sand with a friction angle of about 40 degrees. So calibrating with those 2 cases with our L-pile or group, it's a group model that NSoft has developed. We could also look at alternatives. If we had a softer clay with an undrained strength of about 500 PSF, we would get this load deflection curve for that same group. And if we compacted it to like 95% or of the Proctor maximum density, 96, something like that, we would get an even higher resistance, something like this. So in that case, if you've got a softer clay and you have a really good compaction, you could see 100% increase in lateral resistance. So conclusions about compacted fill is that replacing the clay with compacted sand can show a significant increase in lateral resistance at fairly low cost. The strength gain depends on the contrast in soil strength. We could see increases of maybe 30%, up to 30% with sand, in our case, 93% compaction, up to 100% increase with lower strength material with higher sand compaction. Okay, let's move up to something that's a little higher tech in the ground improvement, jet grouting treatment. Here we have 8 grout columns. They were designed to produce a 5-foot diameter of soil creep, let's call it, mixture of soil and cement and water, which in this case would almost fully encapsulate our pile group underneath the cap. We're expecting that this would extend out 2.5 feet in front of the cap and go to a depth of about 10 feet below the base of the cap. Okay, and we did another test where we had 7 jet grout columns. These were placed on one side of the group only, not the entire group. These are 4 foot in diameter, and they could, with the jet grouting, they could go underneath the cap and treat right up against the first row of piles here. So this was about 13 feet long, 7 feet in the direction of loading, and about, again, 10 feet deep. Here you see the jet grout rig in place. We covered the pile cap up with soil to not damage it, and drove on here and did the work. Here you see the pipes that have 2 dual pipe systems, so you can inject air around the perimeter and slurry cement and water in the inner pipe, so that you can, this air jet constrains the slurry mix to get better mixing. And we had 20% by weight of cement in this case. We checked the compressive strength of the soil with wet grab samples and core samples. This is prior to treatment, we only had a few PSI, 3 to 5 PSI strength of the soil. After treatment, we're up here in the range of, from our test, maybe 400 to 600 PSI. From the design strength, because it's mixing, they typically use a factor of safety of 3 or more, that 2.5 or 3, that gets them down here. So we would have a design strength of maybe 150 to 250 PSI after treatment with that sample. Core samples showed a little bit lower values. Now, in addition to this jet grouting that we're going to talk about here, we also did a kind of a low-tech soil mixing treatment on one face. This would, what we did with a trackhoe, but the soil mixing that you could do here with a variety of techniques doesn't get up in between, underneath the cap against the piles, and it doesn't treat underneath right up to the piles like jet grouting could do. So this is the contrast between, basic soil mixing and jet grouting. Soil mixing, there's a variety of techniques, but this is one that you could use with a trackhoe to get down to maybe 20 feet without too much trouble. You have a feeder that goes, injects the material into the ground, and this shows a video or a photograph of how that might be done. So in our case, we mix this with a trackhoe, just putting cement in at the surface and mixing the whole thing together. In our case, we were at about 10% by weight of cement. Then this would be the area of the pile cap. So this is about 13 feet long, and the width of the bucket, which was maybe about 4 feet, something like that. And we've got a strength from our core samples of about 145 psi of this mixture. So what kind of improvement do we get from just this simple soil mixing, comparing the virgin treatment, which was giving us about 275, we are seeing an increase of 170 kips just from that really simple process. So that's a 60% increase in lateral resistance. Really pretty substantial from a very simple approach. What happens with jet grout under the cap? Now going from the untreated 270 kips, with that jet grout treating, now we're up to 800 kips of lateral capacity. So that represents a 180% increase in lateral resistance. Really a dramatic increase compared to what the resistance we were getting with 9 piles in this thing. Very substantial. You might ask, what happens if we just treat it on one side like we showed there? We get almost as much resistance as we had from treating that whole area under here, because that volume we're pushing against is pretty large on the opposite side. And here, if we look at it in the range where we're testing, 170% increase, or 400 kips higher for comparable displacements. So it's looking like to us that this could be a really important way of increasing resistance. So we got to think about the economics of this. The soil mixing and jet grouting produces substantial increase here. And to get the same increase, we need maybe 9 additional piles, so twice as many piles from soil mixing, and maybe 18 to 20 piles, or 2 times as many piles as we had with jet grouting. And of course, more piles requires a larger pile cap, which also increases our cost. And so our economic analysis says that the soil improvement approach would significantly increase lateral resistance and be more economical than adding more piles. So we went forward and looked at, tried to calibrate our numerical models. So we did that with, here's the virgin clay with this 3D finite element model, Adina, and we're getting good agreement. We had to play around a little bit to do that. Then we used the same model that was calibrated now to look at mass mixing on one side. Got good agreement now there with the model, and similar thing for jet grouting below and around the pile group. Knowing our model was now calibrated, we could look at parametric studies that look at different depths of improvement. You can see it, putting it deeper in the ground gives you more lateral resistance, but there's a kind of a reduction in effect with depth. This is the effect of with depth of putting it on another, on the outside edge. Again, we're getting a decreasing return with distance. If you look at it with on the outside, just putting it on the outside edge here, you can see that there's some increase relative to the untreated zone. Get it deeper, you see improvement maybe up to 40%, depending on the depth you put in. When you put it around the whole zone with soil mixing, you see a much steeper slope. So this would be more effective than just putting it around the outside edge where you're not getting close to the pile. And then we looked at length and got some parameters here. So what's going on in the real world? What we're seeing here is not that the piles are just pushing into the soil or pushing into the soilcrete like we expected prior to doing any testing. But what we're seeing is this whole block of soil is moving together as a super pile, we might call it, with this block reinforced by the steel pipe piles. So I've exaggerated this, but we're seeing resistance coming from passive force on the front face of this soilcrete block and side adhesion from the interface between the block and the soil, in addition to our soil pile interaction here. And we were able to find out from our numerical model that if we got the unconfined compressive strength of this block higher than about 75 psi, that this same mechanism worked for almost all our tests. So we're, in our analysis, we're suggesting that lateral resistance is a combination of the lateral pile resistance that you could calculate with a simple L pile or a group model, the side shear on the side of the soil mixed volume, and passive force on the face of the soil mixed volume. For the lateral pile resistance, we could use PY analysis to get shear and moment. For the side shear, we could assume that our resistance would be mobilized after about a 1/4 inch of movement. This is typical of interface shear resistance. And for our passive resistance, we are finding from our tests that maybe we develop full resistance at 3 to 5, a displacement equal to 3 to 5% of the height of the wall. And we could use a fairly simple model to account for this. We are assuming if this is our soil improvement adjacent to the cap, we could have a shear zone that moved out at 45 degrees and projected down at 45 degrees, and we'd apply shear resistance on those sides. If we treated the soil all the way down, we could get our resistance due to a side shear on the block going down a depth equal to the width of the improved zone, and then extend it out at 45 degrees out to where we come to the edge of the pile cap, and use that to calculate our passive force again. So some of our conclusions: soil improvement can cause a large increase in resistance, maybe 60% for a soil mixed wall, 180% for jet grouting techniques. The pile tend to act as a super pile with resistance being provided from pile interaction, side shear, and passive resistance on the soil. And soil improvement is likely to be a less costly alternative and less time consuming than adding more piles and a pile cap in many instances, and should be considered in the design. I think I've probably gone a little over, so I don't know if we'll have time for questions, but I'd be happy to do that if we have time.
All right.